Okay, so this is a review problem number one. We got a lot to get through in about 15 minutes, so let's get to it. So, first thing, as always, that you're going to do is create your given and find. Now, a lot of your given is going to be done on the picture itself. You're going to see me do that here in just a second. Another thing that's going to slightly change is I don't like to use initial and final when, as you can see right here, initial and final are going to change potentially like 3-4 times. So a lot of times when I'm listing them, rather than call this, say, velocity initial, I'm just going to simply call this the velocity at A, which is 20 meters per second. Okay. Then, as I mentioned a second ago, I like to draw on the picture for certain things. For example, it tells you that this particular section has a mu value of 0.15. It says that sections B to C, and I believe also C to D, are frictionless. So let's just go ahead and say mu is equal to 0 or something to that particular effect. And then this section over here, it eventually says that mu is equal to 0.51. I believe the only other given, unless I am mistaken, is that it also tells us what the velocity is right here at the top of the hill. So I'm just going to go ahead and write down that the velocity at B is 15 meters per second. I'm going to go ahead and check my notes to make sure I didn't miss anything else. Yep, that's it. All right, A. Now, I'm going to skip a step for the sake of time that I will tell you this in all my notes and that you definitely need to do on all of your problems, and that is the plug-in part. Okay, I've seen a lot of people kind of be skipping that, and that was terrible English, but I need to be able to see it to be able to follow what it is exactly that you're doing. So, for starters, change in kinetic energy. This is always kinetic final minus kinetic initial. So in this particular case, it's going to be 1/2 mass the velocity at B squared, because B is the final. If you want to write V final, that's fine. Minus 1/2 mass velocity at A squared. Okay, just final minus initial. There's no other reason. I could see where you would possibly get confused because that's equal to work net, but we don't need to do. We have everything we need to solve that. So right underneath here, you're typically going to plug those numbers in, that being 2.5, that being 2.5, that being 15 squared, 20 squared. And what you should end with is, let me see my notes here as well, negative 218.8 joules. Okay, part B. Part B says do a force diagram on this particular section. We should have force gravity down. That's usually pretty easy for people. We should have force normal kind of up and to the left. By the way, if you drew this on the picture, that's probably going to be a little bit easier for you. For my sake, I'm just going to do it right here. And force friction back down the hill. Biggest mistake made usually on this particular part is people put a force up the hill, usually citing that, well, then how on earth did the thing get up the hill? And the answer is it was already moving at 20 meters per second. That's how it got up the hill. It's got that inertia taking it up the hill. Remember that forces don't tell you which way it's going. Forces point in the direction of acceleration. So that's a general look at it. Obviously, my drawing is not great right there. Part C then says go find how much force friction is. In order to do this, you pretty much got one method, and that's going to be summing the forces. Reminder that you're probably going to need to shift the axis if shifting the axis is an issue for you. There's other videos that I've used on this, and we can talk about that individually, but it should be sum the forces either perpendicular or in the new y. We'll use the new y as acceleration on the y, mass times acceleration on the y. That's all equal to 0. Should be force normal minus force gravity in the y, because we've shifted it, is equal to 0. So force normal equals force gravity in the y, which is equal to mg times the y right here is adjacent to that angle. Not super easy to see. So that should be cosine of the angle. And force friction is always equal to mu times force normal. So you get your answer there, plug it in there, multiply by that. Or you can say mu times m times g times cosine theta. Plug all of that information in there, and you should end up with 3.45 newtons on the part D. Now we find the acceleration, so we're just going to go ahead and sum the forces in the x, and there's your acceleration right there. So we come back here and we see that that's negative force friction minus force gravity in the x. This second part here is kind of easy to forget because you just see this along the axis, but you can see that force Friction in the x is also going backwards, and that's why it's negative. And if I divide both of those by mass, I'm going to get acceleration. This force gravity in the x should be mg sine theta. I'm not going to write it all out again for the sake of space and time. But that's minus 3.45 minus 2.5, 9.8 sine of 20 divided by 2.5, and your acceleration should be negative 4.73 meters per second squared. All right. Next, the question is how much work is done by friction. Now, there are a couple ways to potentially do this. The first way is that you can use the work net kinetic energy theorem. Okay, that's a little bit hard because you'd have work of friction plus work of gravity equals change in kinetic energy, and you could go do that. Actually, yeah, you could do that. And then you just subtract the work of gravity over here, and that would give you work of friction. That's probably not our easiest bet. It might be kind of confusing. The other thing that you can do, sorry, I'm getting ahead of myself here, is that for part E here, work of friction is just equal to force of friction times displacement times cosine theta. Now you might say, well, I know force friction. I even know the angle. That should be 180, which gives us a -1 on that. Okay, because the object is going up the hill and friction's going back down the hill. They're separated by 180 degrees. But you might say don't have displacement, and you might also be confused because F asks you for the displacement of the hill. But quite frankly, you can usually go out of order on these, and you got to know that you got to be able to go find what you need. So we have a 1D kinematics problem. 1D because it's going in a straight line. The initial velocity is 20 meters per second. The final is 15 meters per second, and we just found out that this is negative 4.73 meters per second squared. There's our three kinematic variables. So we have VF squared equals VI squared plus 2A delta X. None of this cancels, so it should be VF squared minus VI squared all over 2A should equal delta X. Once again, plug your numbers in. That's 15 squared minus 20 squared over 2 times negative 4.73, because we're considering vectors. And displacement should end up as, what are we at? 18.5. Is this right? Is this F? Yeah. 18.5 meters. Now we come back down here. We get that the force of friction is 3.45 newtons. Oh, I said I wasn't plugging stuff in. There I go. Times 18.5 meters times -1. A quick reminder. Everything to this point that I've been doing has been a vector. You've seen me take care of, well, other than kinetic energy there. You've seen me take care of direction. Up here, this should be negative, and the negative acceleration because the direction cancels it. Notice I don't make this negative because it's work, and that's scalar. The negative comes from the angle right over here. So that is completed through F. Let's go ahead and scroll down here and see if we can't knock out G. The great thing about G is actually it's relatively simple. It says, what is this height right here? Okay. Sometimes we can overthink stuff. You might go, oh, that's an energy thing or something like that. Well, we just found out this side of a triangle, and we know that angle right there. So this is just a fairly basic trig problem. We know that the total distance right there is 18.5 meters, and that angle is 20 degrees, and it wants to know that side. We'll call that H1 or whatever it is on there. And so H should just be equal to 18.5 sine 20 degrees, or equal to 6.3, is that it? 33, I think, meters. There you go. Okay, next part, part H, asks you to draw a force diagram between B and C. You'll remember that there is no friction, so your force diagram is really easy. Force of gravity down, force of normal up, and that's it. Remember, there do not have to be forces in the direction of the motion, just in the direction of acceleration. This is actually going to be a balanced force, which makes part I very easy. If the velocity right here is 15 and there is no friction in between, then the velocity at C should be 15. I guess all the work I would say you really probably need to show for that is just, hey, velocity at B is equal to velocity at c. So the answer is 15 meters per second. Then we move on to J. As I look at this kind of crazy shape right here, I can be pretty darn sure that the force diagram is not going to stay the same. That means it's definitely going to change its acceleration, which for starters completely rules out kinematics. It really kind of rules out forces, and also kind of rules out a certain part of energy. The main spot of energy and the fact that there's no friction in there kind of should lead you to believe that J, you should be using conservation of mechanical energy. We're not really dealing with springs. I used the initial and final. I guess I really should say C there and D. The potential energy of gravity at A plus the, A, I just said C and D, and plus the kinetic at C is equal to the potential of gravity at D plus the kinetic at D. Fill in those equations, mass times gravity times height of C plus 1/2 mass velocity C squared equals mass times gravity times height at D plus 1/2 mass velocity at D squared. There is a mass at every term, so it'll cancel out. And now we are going to be solving for the velocity at D. We just found the velocity at C was 15. We also very recently found out that the height of C is 6.3. And we know the height of D, it's given to us in this picture right up here as 8 meters. So this is just an algebra problem moving things around. I'm going to subtract that on the other side. I usually like to put these together. Plus 1/2 velocity C squared is equal to this 1/2 VD squared. So let's just go ahead and multiply everything by 2. Square root everything. And that's going to give us VD. If you've done that correct, your final velocity at part D should be equal to 13.87 meters per second. This is about the time I should probably bring up the fact that you might get some rounding. Because of rounding, get some slightly different answers than me, and that is completely okay. Like if you're pretty close to that, I wouldn't worry too much about it. All right. Now we have find the kinetic energy at D. That should be pretty darn easy to do because it's just plug and chug. Okay. The kinetic energy at D is equal to 1/2 mass velocity at D squared. I think the biggest thing you might make a mistake on is you notice like masses cancel here, and so you might cancel mass there, which you don't for this. And that should be 240.3 joules if you plug everything in correctly. L asks for what's the force diagram in this last section. It should look very similar to B and C with one major caveat, and that is there should also be friction going back the other way. Okay. Let's see. Now we have M. What's force friction on that spot? Well, we sum the forces. Once again, this should be even easier than before because we don't have to shift the axis. And the force normal equals force gravity equals mg. Force friction equals mu times force normal. So that's going to equal mu times m times g. Or, if I'm not mistaken, the answer is 12.5 newtons. Sorry, I'm kind of hustle here because my program stops at 15 minutes and I have 1.5 minutes left. Then it wants to find the time and displacement and power. Okay, so that's all I have left. I have time. You have two ways to do this. Firstly, you could go find acceleration. You could sum the forces in the x to get the acceleration. Through acceleration for both n and o, you then just use kinematics. If that's the case, your acceleration should be just writing this down, negative 2.77. I'm just going to rough write this out to give you guys the answer so you can see it. And then you just three equations into your kinematics, and you'll get that the time should be 2.77 seconds. Oh, I'm sorry. I think I misspoke. Acceleration is not 2.7 seconds. Acceleration, I'm sorry. I screwed up. This acceleration is -5. Time is 2.77 seconds if you've done it right. And your final displacement should be 19.2. If you have done that, you could also do it this other way, though, where you do impulse momentum, and then you could use work kinetic energy theorem. Final thing is work over time to get power. Your work is just going to be this 240 over here, because the work, 240 right there, because the work kinetic energy theorem divided by 2.77 gives you your final answer of 86.5 watts.